This is part 1 of lecture 4.4, one-to-one and onto functions. In this video, we will define a one-to-one function, learn how to prove if a given function is or is not one-to-one, and relate the property of being one-to-one to the operations of composition and inversion. Given a function f from a set A to a set B, f is said to be one-to-one or injective or an injection if and only if for any elements x1 and x2 of the set A, if f of x1 equals f of x2, then x1 is equal to x2. It follows that f is one-to-one if and only if for any element y in the range of f, there is exactly one element x in A such that y is equal to f of x. That is, for any element y in the codomain B, y has at most one pre-image. We will sometimes use the following notation to denote that f is a one-to-one function from A to B. Here are some Venn diagrams illustrating some one-to-one functions. For a function to be one-to-one, the only requirement is that no two distinct elements of the domain have the same image. This is clearly satisfied by the two functions shown here. Note that it is not necessary for the range to be equal to the codomain. Hence, the function on the right, in which there is an element of the codomain that has no preimage, is still one-to-one. The two functions at the bottom are not one-to-one because for each of them, there are two distinct elements in the domain that have a common image. It follows from the definition that for any non-empty set A, the identity relation on A is an injection from A to itself. This follows from the fact that the image of any object A under the identity relation is itself. Also, the empty relation is an injection from the empty set to itself. Indeed, observe that the empty set is equal to the Cartesian product of the empty set by the empty set. Let F denote the empty relation. The statement for any objects x1 and x2 in the empty set, f of x1 equals f of x2 implies that x1 equals x2, is equivalent to the statement for any objects x1 and x2. If x1 and x2 are elements of the empty set, then f of x1 equals f of x2 implies that x1 equals x2. The statement x1 and x2 are elements of the empty set is clearly false. So the conditional if x1 and x2 are elements of the empty set, then f of x1 equals f of x2 implies that x1 equals x2 is true. This holds for any x1 and x2. Hence, the entire quantified statement is true, and the empty set is indeed an injection from the empty set to itself. Consider the function f consisting of all ordered pairs xy of real numbers satisfying the equation x plus y equals x times y. We claim that f is a one-to-one function from the set of all real numbers not equal to 1 to the set of all real numbers not equal to 1. That is, for any real numbers x1 and x2 not equal to 1, if f of x1 equals f of x2, then x1 equals x2. We have proved in an earlier example that f is a function from the set of all real numbers not equal to 1 to the set of all real numbers not equal to 1. It remains to show that f is one-to-one. To do this, let x1 and x2 be arbitrary real numbers not equal to 1, and assume that f of x1 equals f of x2. we need to show that x1 equals x2. Let y denote the common image of x1 and x2. Then, by the definition of f, x1 plus y equals x1 times y, and x2 plus y equals x2 times y. So, x1 times y minus x1 equals y, and x2 times y minus x2 equals y. Thus, x1 times y minus x1 equals x2 times y minus x2. Hence, y minus 1 times x1 equals y minus 1 times x2. Since y is not equal to 1, y minus 1 is non-zero. By the cancellation law for multiplication, x1 equals x2. This proves that f is 1 to 1, as claimed. Consider the function g consisting of all ordered pairs xy of real numbers, satisfying the equation y equals x squared. We claim that g is not 1 to 1. That is, it is not the case that for any real numbers x1 and x2, if g of x1 equals g of x2, then x1 equals x2. Equivalently, there exist real numbers x1 and x2 such that g of x1 equals g of x2, but x1 is not equal to x2. Indeed, consider the real numbers 1 and negative 1. Then g of 1 equals 1 squared, which is equal to 1, and g of negative 1 equals negative 1 squared, which is also equal to 1. However, 1 is not equal to negative 1. Therefore, g is not 1 to 1. Let us now look at how the property of being 1 to 1 affects the composition of functions. Given functions f from a to b and g from b to c. If f and g are 1 to 1, then the composite function gf is 1 to 1. If the composite function gf is 1 to 1, then f is 1 to 1. We first prove statement 1. Assume that f and g are 1 to 1. We need to show that gf is 1 to 1. That is, for any two elements a1 and a2 in the set A, if gf of a1 equals gf of a2, then a1 equals a2. To do this, let a1 and a2 be arbitrary elements in A, and assume that gf of a1 equals gf of a2. We will show that a1 equals a2. Recall that gf of a1 equals g of f of a1, and gf of a2 equals g of f of a2. So the previous equation becomes g of f of a1 equals g of f of a2. Since g is 1 to 1, this implies that f of a1 equals f of a2. And since f is 1 to 1, this in turn implies that a1 equals a2. Therefore, the composite function gf is 1 to 1, which proves statement 1. Next, we prove statement 2. Assume that the composite function gf is 1 to 1. We need to show that f is 1 to 1. That is, for any elements a1 and a2 in A, if f of a1 equals f of a2, then a1 equals a2. To do this, let a1 and a2 be arbitrary elements in A, and assume that f of a1 equals f of a2. We will show that a1 equals A2. Since f of A1 and f of A2 are equal, their images under G are also equal. That is, G of f of A1 equals G of f of A2. Since G of f of A1 is equal to GF of A1, and since G of f of A2 is equal to GF of A2, the previous equation is equivalent to GF of A1 equals GF of A2. Since GF is one-to-one by our hypothesis, we must have A1 equals A2. Therefore, F is one-to-one. It is not true in general that if the composition GF is one-to-one, then the function G is one-to-one. To show this, we need to give specific functions f and g such that the composition GF is one-to-one, but G is not one-to-one. Consider the functions f and g from the set of real numbers to the set of real numbers, where f is the natural exponential function and g is the absolute value function. Then the composition GF is also a function from the set of real numbers to the set of real numbers, with the image of every real number x given by g of e raised to x, which is equal to the absolute value of e raised to x, which is equal to e raised to x. We know from pre-calculus that the natural exponential function, which is the function GF, is one-to-one. However, the function G is not one-to-one, since, for instance, 1 and -1 are distinct real numbers with the same absolute value. Therefore, the functions f and g are the desired counterexample. Recall that if f is a function from a to b, it is not true in general that its inverse relation is a function from the range of f to a. This next theorem gives a necessary and sufficient condition in order for f inverse to be a function. Namely, f inverse is a function from the range of f to a if and only if f is one-to-one. The condition f inverse is a function from the range of f to a is equivalent to the condition for any element b of the range of f, there exists a unique element small a in capital A such that the ordered pair BA is an element of f inverse. The condition f is one-to-one is equivalent to the condition for any elements a1 and a2 in capital A. If f of a1 equals f of a2, then a1 equals a2. We begin with the proof of the forward implication. Assume that f inverse is a function from the range of f to a. To show that f is one-to-one, let a1 and a2 be arbitrary elements of the set A. Assume that f of a1 equals f of a2. We need to show that a1 equals a2. Let small b denote f of a1 and f of a2. Then b is an element of the range of f, and the ordered pairs a1b and a2b are elements of f. So the ordered pairs b a1 and b a2 are elements of f inverse. Since f inverse is a function from the range of f to a, this implies that a1 and a2 are both images of b under f inverse, and hence a1 equals a2. Therefore, F is 1-to-1. For the converse, assume that F is 1-to-1. Let B be an arbitrary element of the range of F. We need to show that there is a unique element in the set A that corresponds to B under F inverse. To show existence, observe that by the definition of range F, there is an element small a in set A such that the ordered pair AB is an element of F. So the ordered pair BA is an element of F inverse. This proves existence. To show uniqueness, let A1 and A2 be arbitrary elements of the set A and assume that the ordered pairs BA1 and BA2 are elements of F inverse. Then the ordered pairs A1b and A2b are elements of F. So B is the image of both A1 and A2 under F. Since F is 1-to-1, it follows that A1 equals A2. This proves uniqueness. Thus, F inverse is a function from the range of F to A, which completes the proof of the theorem. You have come to the end of part 1 of lecture 4.4. You may now proceed to part 2. Thank you for your attention.